Let me present our report, which is called Combined Lossy Compression to Frictional Images, that has been prepared by me and my colleague Viktor Makarichev via the Department of Information Communication Technologies of National Aerospace University, Kharkiv, Ukraine. And the presentation outline is here. So, first of all, I would like to say some words about what are frictional images and what are their characteristics. Then requirements to compression. Then a few words about compression based on discrete atomic functions. Then I will give details about the proposed approach to lossy compression. After this, there are a few slides about the results for images of different complexity and optimal parameter selection. And finally, the conclusions will be given. So, there are different types of frictional images. I would like to give 3 examples. First of all, these are conventional color images represented, for example, as RGB data. Another case is medical color images, for instance, retina images. And the third case are remote sensing images in visible band, which can be data from multispectral remote sensing, as example. And 2 examples of remote sensing images are given at this slide. And one typical feature of such kind of images is that they have quite a large size. The image size might exceed several megabytes and even tens of megabytes. And because of this, compression is desired for transmission of such data via communication lines, and as well as for their storage. I would like to remind some basic requirements to compression. First of all, it is often desired to provide high compression ratio with appropriate quality. I say about quality with respect to lossy compression, for which some distortions are introduced into data. Second, compression should be performed quickly enough, both compression and decompression. Third, it is often needed to control quality of lossy compressed images, and this control should be done quite easily in order to provide a desired quality of compressed data. But these are, let's say, general requirements. At the same time, there can be additional requirements. First of all, it is often needed to provide privacy of compressed data. In particular, in medical image compression, it is desired to somehow hide information for patients, about this. Next, it is desired to have different compression options, lossless and lossy. I will tell a little bit about this later. Then, it is often needed to save power needed for compression, especially if compression of remote sensing data is carried out on board of drones, on board of UAVs, and so on, because power is limited in this case. This also has a relation to the so-called green technologies. That is, we have to save energy and not to irradiate into the space around us. So, some words about discrete atomic compression. It is, in general, it is a lossy image compression algorithm. And it is based on atomic functions, which are specific type of wavelets. Discrete atomic compression provides better compression than JPEG, and even better compression with some other modern compression techniques under condition of the same quality of compressed image. And what is also a good property of discrete atomic compression is that privacy protection can be integrated just into compression due to use random and unknown to other person configuration of blocks. Here are some papers where you can find details about discrete atomic compression. And let us look at the structure of compression based on discrete atomic function. So it is, let's say, quite typical. We have RGB matrix, or let's say frictional image. We perform RGB to YCRCB conversion. Then we apply discrete atomic transform. After this, having coefficients of discrete atomic transform, we carry out quantization, and just at this stage we introduce distortions. And after this, we can use Huffman codes and run lengthened coding or some other method of coding the quantized coefficients of our transform. The compression is in inverse order. That is the coding, the quantization, inverse discrete atomic transform, and the conversion from CRCB to original space. What we propose and why do we propose this? It is often desired to have both modes of compression, lossless and lossy. For instance, you know that JPEG has JPEG LS and other known standards also have lossless and lossy compression modes. And our idea is the following. Let us get a lossy compressed version and then calculate a difference image and compress difference image in a lossless manner. In this case, we have DAC file that has header. It has the main part, and this is the part that corresponds to lossy compression. And then we have also the extension, and it contains compressed differences. Due to this, we can first get a lossy compressed image, and if this lossy compressed image does not satisfy us because of several reasons, then we can ask, okay, please get the extension, and we can get a lossless compressed image. Concerning compression based on discrete atomic functions, we have to say that there is the parameter called UBMET that controls compression. So setting a larger UBMET, we get more distortions introduced, and at the same time more a larger compression ratio for lossy compression. And for this case, we have earlier considered compression results for a large database of frictional images provided by European Space Agency, and the following results have been obtained. So there is optimal point that corresponds approximately to UBMET equal to 63, and arithmetic coding applied to differences, it performs better than Huffman coding and run lengthened coding. And you can see that we have a certain benefit compared to zip coding, for instance. But at the same time, these are average data for a large number of images. But at the same time, the question is the optimal the same for any image? And this was the main question in our study. So we considered several images of different complexity. Here are the results for images of complex structure. And for images of complex structure like this presented at this slide, at this image. So, and we also have analyzed 3 versions of compression based on the discrete atomic transform. This is classical version, DAT with block splitting, and DAT with chroma subsampling. 3 different approaches, and we have compared them. So the conclusions concerning complex structure images is the following. like for classic DET and DET with chroma subsampling, they produce similar results in terms of lossless compression ratio. Lossless compression ratio is in the last column. At the same time, classic DET produces better PSNR, peak signal to noise ratio, and mean absolute deviation, but it produces slightly worse lossy compression ratio. And one important aspect is that lossless compression ratio is practically the same for UMAT equal to 63 and 95. So we have a, let's say, quasi-constant region of UMAT, and we can take UMAT from this interval. At the same time, DET with block splitting, it produces worse results than two other considered modes. Because of this, we can say that for complex structure images, it is worth using classic DET version with a MAT about 90. And this selection, this recommendation, provides a reasonable trade-off between the quality loss of compressed images and the compression ratio of a lossy and lossless modes. The next part of our study deals with simple structure image, like this image. And we say that this image is simple structure because it contains a large portion of homogeneous, of pixels belonging to homogeneous regions. And in this case, the situation is slightly other. Classic DET and DET with chroma subsampling again produce similar results, but at the same time, DET with block splitting produces the same results as classic DET, and here you can see that it produces larger compression ratios. So we can recommend to use DET with splitting with UMAT about 150, since it produces a reasonable trade-off between quality of lossy compressed images and compression ratio for both modes. A question is how we can characterize complexity of images. One way of characterizing complexity of images is to use entropy as parameter able to characterize image complexity. Then we have analyzed the obtained results and detected that for complex structure images, lossless CR can be about 1.25 and lossy compression ratio from 2.5 to 5. PSNR is about 35 dB, and this is at the edge of distortion visibility. Meanwhile, for simple structure images, lossless CR can be up to 2.7. That is considerably larger than for complex structure images. Lossless CR can be about 15-20, and PSNR is about 42 dB. That is introduced distortions are invisible. And we would like to change in the future, we would like to design an adaptive method of complexity characterization based on entropy or some other parameter. Then we have also analyzed what is computational efficiency. Here are the parameters of our computer used in this case, and the conclusions are the following. For images having tens of megabytes, the tens of gigabytes, the computational efficiency is high enough, and the compression and decompression take only a few seconds. The compression is faster than compression. And one more conclusion is computational time is approximately linear proportional to the image size. You see that for an image of about 100 of megabytes, we need the largest time for both compression and decompression. So finally, what are the conclusions? We have proposed and analyzed the combined loss approach to compressing color and free channel images, and have understood that it is practically the same, almost the same what UMAT to set, but setting a larger UMAT, we can provide a larger compression ratio of lossy compression. We have given recommendations of parameter settings, and we have also compared our method with zip, RAR, and PNG. And the results are that our method provides practically the same efficiency of PNG with compression level 9. Some details concerning computational time are given, and we can see that our method is fast enough. Thank you for your attention, and you're welcome to have some questions to me, please. Colleagues,
I think that everything is clear.
Okay, if no questions, then we can come to the next presentation.